A couple reminders. We've got 3 quizzes now, 4, 5, and 6 that I posted last week, and they're due this Friday. Seems like a lot, but they're short. I think 2 of them are 5 questions and 1 of them is 7 questions. And those will cover the last 3 units, sequential logic, timing analysis, and the topic I'll cover today, digital building blocks. Make sure you don't forget to upload your Lab 3 and 4 demos. Charles posted instructions for what to include in your Lab 4 demo video, and we've got submission boxes for those. And we'll have our final exam a week from today on Monday, December 6th. I'm going to give the final exam on Dropbox as I did the quizzes, and it'll be available all day. I'll give some more details about that in a minute. And then if you're a graduate student, we have the graduate lab, which is basically a fairly simple variation on Lab 4. And the details of that are also posted on Dropbox. I posted the video that I produced last fall that describes that. And there's a lot of details in there. If you have any questions, let me know. As far as submitting it, you just upload it. Upload your tar file as you did for Lab 4, and then the demo will be the same as it was for Lab 4. Okay? So for the final exam, the Dropbox will give you 120 minutes to take it once you start it. There's 1 attempt. There'll be 25 questions, which is 4.8 minutes per question. And it will be comprehensive, and it'll cover six topics. The RISC-V instruction set architecture, so those will be like, assembly language questions, basically. System Verilog, so there'll be questions about, finding bugs in Verilog or answering questions about System Verilog snippets. Next part is pipelined microarchitecture, which is essentially the CPU design from your lab. And so there's control signals. How do you set control signals for specific instructions, that kind of stuff. And then I think the midterm covered those three topics. And then since the midterm, we've had sequential logic, which are state machines, timing analysis, and digital building blocks, which I'll talk about today. Now I posted a study guide for this on Moodle, on Dropbox. I have 2 documents, 2 PDFs that you can download. One of them is just a list of questions. These are questions that I've given on final exams in previous semesters. And then there's another document that has the questions and the answers. Now, some of the questions are a little, in terms of the topics are all exactly what will be covered on the final exam for this semester. There's a few questions, I think, where instead of RISC-V, it's the MIPS CPU, but the differences are very minor. So like I think I have one question where I give you a block diagram of the class CPU when we were doing MIPS, but it's very similar to the RISC-V, and you should be able to still benefit from looking at that. Of course, you guys know MIPS hopefully from CSCE 212. And then of course you can use the quiz, the prior quiz questions as well to study. So there's quite a few questions on there. I think there's like 25 pages of questions. Basically, I took all my previous final exams from recent years and put them in there. And then for the final exam, I'm going to be mostly just mining those, asking very similar questions. Okay? If you have any questions about any of the study guide questions, then feel free to send me an email. Okay, so today we're going to talk about, this will be our last lecture, we're going to talk about digital building blocks, which are basically common digital subcircuits that you'll see when you're doing HDL design. We'll start with adders. So hopefully you remember from your 211 class how to do binary addition. It's basically like grade school addition, where you line up, you have the 2 values that you're going to add, and you line them up where each of the corresponding bits are lined up in columns. And then if the sum of a column is 2 or 3, that will generate a carry into the next column. So these are called column. A column is a bit position in both the A and the B operand, right? And as well as a bit position, the corresponding bit position in the sum. And then you guys, I'm sure you remember the full adder circuit. So full adder matches up to the behavior of a column. So you have a carry in from the column to the right, and then there's a carry out that goes to the column to the left, right? And so basically you end up with 3 input bits, which can add up to a value between 0 and 3. And then the output is 2 bits, which holds a binary encoding of 0 to 3. But the way that's realized is that you have one of those bits as the sum, and the other bit is the carry out, right? Okay. So you probably also talked about how to use full adders to create a ripple carry adder, which is where you instance one full adder for each column or for each bit for your adder. So if you have a 32-bit adder, you'll have 32 of these. And then you'll have the carry out of each column will be fed into the carry in of the column to its left, right? And then the sums, of course, will be sort of taken together as one multi-bit value, right? The problem with this is that it's slow, because the problem here is that the latency of this guy, so that meaning from the time the inputs come in to the time you have a result, is going to be the latency of an individual full adder multiplied by the number of bits. So when you're doing your timing analysis, like we talked about in the last lecture, that's the latency, that's the propagation delay of the full adder. And this is, it's not good. And it scales up, with the number of bits. So one way you can attack this problem is, instead of having the carry ripple all the way through the adder chain, you can basically group together sets of consecutive columns. And then for each one of those sets of columns, you can generate a carry out from that whole group in a more efficient way than just propagating the carry all the way through the columns. And that's called a carry lookahead adder. So the idea is that each column, in addition to producing the sum and the carry out, will also produce 2 additional outputs called generate and propagate. So basically what we're talking about here is we're changing the full adder now. We're changing what the full adder is. The full adder previously was just 3 inputs, 2 outputs. Now we're adding 2 more outputs. And so the generate for column I is the A and the B for column I. And what that means is that if both the input bits for that column are 1, that means that that column is going to generate a carry out irrespective of its carry in. Okay, yes?
By the column, you mean the bit position? Like
right, the bit,
bit 1?
right, yeah. Yeah, so the terminology is a little weird, because when you do grade school addition, you don't call these columns. This is a term that's kind of designed for associating individual positions, digit positions, in both the inputs and the output, as a unit that we're building with a full adder. That's what I mean by column. Not a common term. Okay, so generate is a new bit we generate from each full adder, and the idea is that for each column, generate will be 1 if you're going to get if you're guaranteed to get a carry out from that column. regardless of the carry in. And then propagate is the A for that column or the bit for that column. And what that means is that it basically means that you have at least one input set to 1, meaning that it's not going to generate a carry out by itself, but if it also has a carry in, then that carry in will then be propagated to the carry out, right? So basically what the generate means is that we know the sum is going to be at least 2 out of that column. The propagate is saying we know the sum's at least 1, meaning that if you also have a carry in, that carry in will propagate through, right? So like I said, generate simply means that the sum is at least 2, and propagate means the sum is at least 1, right? Now if the sum is 0, like if A and B are both 0, you're not going to generate a carry, and if you get a carry in, it'll be stopped at that column, right? So generate and propagate will both be 0 if A and B are both 0. Yes?
So if generated 1, it means that we for sure have the carry out, but if propagate is 1, it means that we might or might not have the carry out.
Right, exactly. That's another way to say it. Yeah. Okay, so then you can calculate the carry out of column I by saying the carry out of column I is going to be the generate of column I, right? Or the propagate of column I if its carry in was also 1, right? So it's the generate of sub I or the propagate of sub I anded with the carry in of I minus 1, previous column. Okay? Okay, so the idea is that we have to calculate, if we calculate now you might say, wait a second, hold on here. Hold on. If that's how we're calculating the carry in, that's still just basically creating this chain, right, that's coming through. Okay, so if we calculate the generate and the propagate for all the columns, so in other words, we add this functionality to all the full adders, right? So we're adding some extra logic to all the full adders. Then we can use all those in another logic circuit to basically calculate what the carry out of the whole block is going to be. And the goal is to be able to do it faster than propagating the carry in a ripple carry adder, right? Now, how's that going to work? Basically, the generate for columns 3 down to 0. So this is a block of, we're going to take the low order 4 bits now and sort of group those as one block. And we're going to basically use all of the internal generate and propagates from within that block to quickly figure out what the carry out of that block is going to be, and hopefully do it faster than that ripple carry that would be normally going through in a ripple carry adder, right? Okay, so the way you do that is you basically look at the generate of the most significant bit, generate 3. If that one's 1, then I'm done. If the leftmost bit in the block is generating, then I know the whole block is going to have a carry out. But if there was a propagate on the most significant bit, now I have to figure out if there was a carry in going into that bit. So I have to use this nested logic now, which basically checks the carry in into bit 3. Well, the carry into bit 3 is going to be 1 if the generate on bit 2 is 1, or if there's a propagate on bit 2 and there was a carry in on bit 1, a carry out on bit 1. Well, the carry out on bit 1 is going to be set if the generate on bit 1 is set, or if the propagate on bit 1 is set and the generate on bit 0 is set. Make sense?
Generate on bit 0 is carry
No.
in.
That's generate on bit 0 is just if A0 is if A0 and B0, right? The carry in would be like having a generate on bit -1, right? Now this is actually not considering the carry in. This is assuming carry in is 0. Carry in, the overall carry in is 0. Carry in on 0 is, but you could also add that. You could say,
instead of G0 having some,
you could say propagate on bit 0 or carry in, yeah. Sure, yeah, you can continue drilling down. Okay, so the question is, and that's the generate, and the propagate for the block is going to be, in other words, I want to know if I had a carry in, like for example, carry in 0, right? If that carry in 0 would propagate all the way through, that would be if all the propagate bits were set to 1. So propagate 3 and propagate 2 and propagate 1 and propagate 0, right? Make sense? So this is basically just using the internal propagate and generates to figure out what the whole block. So I'm creating this notion of a block propagate and generate. The block propagate and generate is the same thing as the individual bits. It's just applied over a range of bits. Okay? Okay, so so the way this will look is you've got, now let's say for example, I have a 32-bit adder, and I'm going to use 4-bit blocks. Now you don't have to use 4-bit blocks. You could do this with 8-bit blocks or 16-bit blocks. There's trade-offs here. But in this example, in this diagram, they've chosen a 4-bit block. So they've decomposed the 32-bit adder into 8 4-bit blocks. And so they structure it like this, where you still have a top-level carry-in, and you still have carry-out 3, carry-out 7, carry-out 23, carry-out 27, because those are the carries that go from one block to the next, right? And then you can calculate inside this block. The idea is that you want to generate. You want to come up with carry out 3. You can calculate it using the generate and propagates from the internal signals, right? So that looks like this. This is literally just the same thing I just showed you, except I showed you the Boolean logic. Now this is the digital logic diagram. So you can see that you've got to generate 0 and propagate 1, and that's ORed with the generate 1, and then that's ANDed with the propagate 2. So this is just the generate equation. And this is the propagate equation, which is just an AND gate of all the propagates. Okay, and then these guys are then combined with the carry-in of, this is what I was talking about when I answered your question. This is how you would then bring in the carry-in bit 0, right, or the carry-in from the previous block if this was another block. This is referring to block 0, but there's other blocks here as well, right? Okay, so here's where it gets a little confusing. How do we calculate the performance of this circuit, the latency, the propagation latency, the propagation delay? Okay, so for this, you have to find the long path, just like we did, in the timing analysis. So the long path here is going to be, what is the critical path through this circuit? Well, I'm going to start. Well, I got to start with the inputs A and B, right? So from A and B, the first thing I got to do is I got to generate these guys, the individual bit propagate and generates, right? So that's going to be the time it takes to generate the propagate and generate. This is just the individual bits, T, P, G, right? So I got it. This is not actually shown. This logic is not shown in this diagram, but because I have these P and G's here, right? That's how long it takes me to get those. Then I have to add TPG block is this. It's the block for calculating this G, multi-bit G, multi-bit P, right? G 3:0, P 3:0, right? So that's that. Okay, then now here's where this is where we get to the problem with this guy. Then I have to go through this thing, right? Right. Now, the problem is, now this is the part that's a little tough to get your head around, at least in my opinion. All of this stuff, everything I've talked about so far is happening in parallel. Those are all concurrent, right? But after you have that, then you go through this circuit. And the thing about this circuit is it takes the C in from the previous block. Okay, so I have to basically do this stuff. I can do this stuff in parallel, right? Which means I only pay for it once here, right? There's no multiplier in front of these. I only do it once because they're in parallel. But This is not in parallel. This is sequentialized because this C in, right? So what happens is that this T and or, which is just an and or gate, right? That has to be multiplied by n divided by k, where n is the 32 bits in this case, and k is the 4 bits, right? So it's 8, right? So there's 8 blocks. I got to multiply this latency by the number of blocks, because that's still a chain. That's just like the ripple carry chain. The only difference is that now I've increased the granularity, and I'm just going through blocks now. The latency is being defined by the number of blocks, right, as opposed to the number of bits. So that's a problem. That's no good, because that still scales pretty horribly. And there's a trade-off here, because you might say, wait a second, whoa, just increase k. Make k bigger. You make k bigger, you make this multiplier smaller, right? Yes, but if you make k bigger, it's going to make this guy bigger, right? It's going to drastically increase the complexity of this logic, which is you're going to get killed on that term. Yes?
So n is the number of bits of the whole operation, and k is the number of bits in one block.
In block, yeah. So k is the number you choose, and n is basically your.
So n divided by k is the number of blocks, but
right.
why we subtract 1?
You subtract 1 just because you assume that C in, which is on the first block, is given to you at the beginning. You have that instantly, so that's free. So basically this C in, which is the original carry in, yeah, I'm not waiting for that one. That's why it's -1. And then the other thing too is, and this is not a big deal, but k, you also have to get the actual sums, right? And the sums of each block are still being generated using a ripple carry. So the k is still, the little blocks are still doing a ripple carry adder. So, but they're all being done in parallel. So you only have to pay k times TFA. TFA is the full adder. Basically this part from here to here, okay? So that's not too bad, but we could do better. So there's this thing called a prefix adder. And a prefix adder is trying to solve this problem. Trying to get around this. We don't want this to be linear. And you might say, well, I mean, what are you going to do? I mean, the delay of an adder is going to scale up when you go to a wider adder. You're not going to be able to avoid that, right? However, it'd be better, instead of linear growth, if we had logarithmic growth, right? Like instead of just this times that linear factor of n, it'd be better if it was logarithmic log of n, right? So how do we do that? Okay, so that's what a prefix adder is. So basically, a prefix adder is works the same. It's kind of the same principle in the sense that you're calculating the carry outs, or I should say the carry ins, by using propagates and generates, right, from the A and B bits, right? Okay, the difference is that instead of generating them from bit 0 to the left, we can generate them sort of as a tree, where instead of like building it out from bit 0 from least significant to most significant, we can take subsets of bits with subsets of the columns and figure out what the generate and propagates are from those, right? So we can build it up like almost like basically a binary tree, where we can start out with 2 bits, every 2 bits, and then we could take the outputs of those and combine them together, right, to get 4 bits and so on. That's basically the idea. So in this case, we have these generates groups and propagate groups, which are also basically a G with two numbers with a colon that defines the range of columns that we're generating them for. So in this case, C of I is going to be so C of I, what we ultimately want to get, this is the end goal. So let me back up here a minute. The goal here is to calculate CI, which is going to be the generate I minus 1 down to negative 1. Right, now you say, where's negative 1 coming from? Well, negative 1 is the original carry-in, right? Is the column that's, represents what comes to the right of all the columns in the adder, right? So that's what we want. That's what we want to get, right? But we have to build this up, okay? And so the idea is that we want to quickly compute all of the generates we need to get up to that last bit I, or whatever bit, like say bit is, like say 31, right? So we want to be able to calculate bit 0 down to negative 1, and then from this we can get 1 down to negative 1, and 2 down to negative 1, and 3 down to negative 1, so we can build it up, right? That's the idea, okay? And then column minus 1, as I mentioned, is carry-in, is the top level carry-in, right? So G, now this is just a terminology thing, because the carry lookahead didn't consider the carry-in to be G sub minus 1, but the prefix adder uses this as a convention. It says the generate of minus 1 is actually the carry-in. So in the prefix adder, they kind of eliminate this idea of the top level carry-in. They just call that the generate minus 1. Does it make sense? But it's still just the carry-in, the top level carry-in. Okay, and then of course the top level propagate for 0. Propagate minus 1 is 0. Does that make sense? So that's, like I said, that's really just kind of a terminology thing. Yes?
What is SI on the previous slide?
A sum. That's the sum bit.
Oh.
Yeah, A and B are the inputs, and S is the output. The sort of the sum of A and B.
So instead of CI, we put G I minus 1, I minus 1, 2 minus 1.
Right. Yeah. So the idea is that this G I minus 1 to minus 1 is the carry-in. Is the carry-in to this full adder column I, right? So in other words, basically we're kind of eliminating the whole notion of the carry-in entirely. We're just saying we're going to look at the generate from the previous column, and we're going to use that to calculate. You're going to use that as the third input to the full adder, right? Okay, that's what that's saying. Okay, so here's the key for making this work. So if I want to calculate the generate from bits I to j, you have to pick a bit in the middle called k. It's usually, I think it's always halfway, because it's built as a binary tree, as I mentioned. So basically you've got I and k, and the halfway point between I and j, I'm sorry, thank you. I said that wrong. You have I to j, and there's a halfway point called k, right? It's in the middle of I and j, right? So if you're calculating generate from I to j, it's the generate from I to k, which is the left half. You have a range. The left half of the range is, you look at the generate from the left half, and if that generate is 1, I don't care about the right half, right? Who cares? But if the generate of the left half is a 0, and the propagate of the left half is 1, then I have to consider the possibility that I can generate from the right half of the range, right? So again, it's I to j, so the left half, most significant half, is I to k, right? And then the right half is k minus 1 to j, right? Right. So, and then of course the propagate is, they have to both be, if both halves are propagate is 1, then the overall propagate is 1. Now you might say, well, that's kind of just common sense. What's the point of that? Well, that's the way that we're going to build up from just the base level single bit propagate and generates, and we're going to use them to construct this tree, right? And from that tree, we eventually want to get to the point where we can generate a generate for the whole adder. I mean, well, for the most significant bit, basically. Or for each individual bit. Ultimately, we want all the generates. We want generate 31 down to negative 1. We want generate 30 down to negative 1. We want generate 29 down to negative 1, because each of those 32 generates will then be used for the carry-in of all the full adders. So just to clarify, we're still using full adders, right? So each bit is generated by a full adder. What the prefix adder is doing is it's essentially breaking the chain of carries, and it's calculating the carry-ins separately for each of the full adder columns. That's what it's doing. That's the idea. But we still have the full adder. We're just generating the carries differently. Okay? Okay. Yeah, so this is what I just explained. So you've got an upper part. Sorry, I said left half and a right half, but the book says upper part and lower part. I think that's actually better because, well, maybe not. Upper is the left, lower is the right. Upper is most significant, right? Right. Okay.
Which is least significant with this or that?
Yeah, it should be most significant half, least significant half. That's what it should be. That'd be better. Yeah. Okay, so the way this works is, like I said, you start out with, this is a 16-bit example. Okay, so what these boxes represent up here are the boxes on the top are the generate and propagate for each individual full adder. So these are the things, same things we had before with the carry look ahead. Just, like I said, you take the full adder and you get P and G from that. Okay, so that's what those boxes are. Then the black boxes is a way that we can take, we're basically combining, now we're doing this for generate and propagate, we're going to combine two halves into one half, two halves into one whole, right? We're going to merge, right? Now, in the case when you first start out, all you've got is single bits, right? So I'm going to take, for example, bit 13, 14, and 13, right, which I get P and G, and I'm going to merge them together, and I'm going to have a group of 14 down to 13, right? So that's going to give me, the way that looks is it's basically just these three gates. You take the propagate and generates from above, and you combine them together into a group, right? Using the logic, that's the Boolean logic, but this is you're just using this logic here, right, to create a new generate and propagate for these groups. But the cool thing about this is that once you have, say, this first level, I'll have 14 down to 13 and 12 down to 11, for instance, right, by merging those two pairs together. Okay, then on the next level, I can go 14 down to 11 by taking the output of this guy and the output of this guy and merging them together. So I get two groups of 2 bits, and I combine them to get 4 bits, right? But the thing that's even neater is the thing that's a little less obvious here is that this one is 13 down to 11. Now I mentioned earlier, I shouldn't have said this, but I said that K is usually in between, halfway in between, but that's not true. It doesn't K doesn't have to be halfway between I and J, because notice in this case, 13 down to 11, the way I create that group is I grab 13 directly. So I grab propagate and generate for just bit 13, and I can combine it with 12 down to 11, right? So what happens here is I grab this single bit guy, and then I grab this 2-bit guy, and I get 3 bits, right? So yeah, sorry, it doesn't have to be in the middle. You can grab any 2 arbitrary groups of P and Gs to merge them together, right? Okay? And then you can get combinations that are wacky like this one, like this 9 down to -1. Now remember, -1 is just the top level carry in. Well, the generate is the top level carry. The propagate for that one is 0, right? So this one, 9 down to -1, is I take 9 down to 7 as well as 6 down to -1 and combine those together, right? So by the end, I have to go through, well, 4 levels because there's 16 bits and the log base 2 of 16 is 4, right? So there's 4 levels of this, but in 4 levels or log base n levels, I can come up with any I can come up with any value of n down to -0 by combining together combinations of the stuff that came above. Now it doesn't have to come from the immediately previous level though. This is the thing that confused me when I first looked at this, right? You don't have to get, like when you look at this last level, notice that this guy, I'm getting an input from the second level, right? And I'm also getting an input from the third. So I'm combining this guy and this guy. I'm getting a second level group and a third level group and combine them together to get a 4th level group. right? So I think that's kind of cool. You can generate, and then once you have these generates, 12 down to -1, that's your carry in. That's it, you're done. You don't have to worry about ever going back to, like the top level and having to propagate things through. So, and then the sum is generated as, well, this is just a full adder. The only difference is that I'm adding, instead of the carry in, I got the G I minus 1 down to -1. That becomes my carry in. And then the sum is just the sum. Then everything else here is just full adder, right? Just I got my carry in. Okay? Yes?
So when you take inputs from two different levels, you have this asymmetric calculation when you have when k is not in the middle, but when you take two values from the same level, you get symmetric things when k is in the
That's right, but the critical path, but the only thing that matters is the critical path, right? So yeah, some of these, like this guy, 6 down to -1, I'm going to actually get this before I'm going to pick up some of these generates from the third level, and some of them come directly from the second level, and this one comes from the first level, right? So yeah, they're not balanced, but the only thing that matters when I calculate the speed is the longest path, right? But you're right, not all the paths are balanced, that's for sure. Okay, so the time, this guy is time of the propagate and generate, just like before with the carry lookahead. I got to get the the boxes at the top, just the regular single bit PNGs, plus log base 2 of n, right? Obviously, because I go in 4 levels for a 16-bit, and then that's multiplied by the PNG prefix, which is the black box, which is what? That's the combiner logic. That's the merge logic, where you take two groups and merge them. And then you add together the time for an XOR, because you have to go through this XOR. Now you might say, wait a second, there should be, yeah, I know you're going to say, there should be 2 XORs. No, because this guy would have already been done. This guy is in parallel. The first XOR was already, the output of this XOR would have been done a while back, because it only depended on A and B. It's only one XOR, right? So, and that XOR, all those XORs are in parallel too, so there's no multiplier there, right? But it is in series with this black box stuff, the log base 2 times the black box. So you have to add it, because it is in series with this black stuff, but, and it's also in series with the original generate and propagate, but then you just end up with a term that scales with the log base 2 of n. This is the ultimate adder circuit, at least, in terms of what we cover. Okay. Yes?
The propagation prefix, the propagation of the black box, of the black square, right?
This PG prefix? Yeah, that's this logic. It's pretty much just two, it's just, you might say, wait a second, I mean, the critical path of that should just be these two gates, right? Well, yeah, but remember, there's no AND gate in CMOS, so there's actually, this is an AND and an inverter. Yeah, so whatever your critical path is through the black box, that's what this term is. So this scales much nicer than the carry lookahead adder. Okay, so basically, I won't go through all the math is just pretty much just plugging in numbers. But for example, let's compare a 32-bit ripple carry, 32-bit carry lookahead, 32-bit prefix adder. Now the carry lookahead has 4-bit blocks, and as I mentioned, that's something that you can manipulate. You can change k, and for a small adder, you might be actually faster with the carry lookahead if you adjust your k right. But of course, as you go to a 64-bit adder, I don't think you're going to beat a prefix adder just because of the scalability. But anyway, if the 2 input gate delay is 100 picoseconds and the full adder delay is 300 picoseconds, then you just plug in your numbers, and you can see that with these numbers, with these technology parameters, the ripple carry is 9.6, the carry lookahead is 3.3 nanosecond, prefix adder is 1.2. So with these numbers, now again, it depends. There's different numbers where you could get maybe the ripple carry might be fastest for a really small adder. But like I said, generally speaking, once you go to a large enough adder, you're always going to win with the propagate. Yes?
Can you combine 2 types of adder, like having 4 bits lookahead then combine 4 bits with
Yeah, sure. Yeah, you could probably do that. I don't know if it would. I'm not sure under what circumstances that would be better. Because like I mentioned, like with the carry lookahead, these were just ripple carries in here in these blocks, right? And of course, you might say, well, 4-bit, but you could make these like a 32-bit block if you wanted to, right? If you had a really big adder. In which case, you might want to do a prefix adder inside those blocks. And you might end up not getting the fastest adder by doing that, but you may get a better area. You might get better resource utilization. You know, it may be more efficient for you to do it that way if you consider the cost, right? Prefix adder is obviously the most expensive one, because ultimately everything's a trade-off between gates and speed, right? Which we're not considering the number of resources, although that would be a great question. Okay, so all right, so now I'm going to switch gears here and just kind of rattle through some other stuff, some other building blocks. So I think you guys already know this because you technically already have this in your CPU and your ALU from your lab. But a subtractor is where you create a subtractor by building around an adder, and you essentially take the 2's complement of the B input, right? You make it negative, and the way you do that is you invert each of the bits of B, and then the top level carry in is 1. And the reason why we put this in here for 2 reasons. One, it's relevant for the divider that I'm going to show later, but also it also gives you a reason why you'd want to use the top level carry. Like, you know, you might be thinking, who's ever using the top level carry in? Well, it's used for the subtractor, because when you do a 2's complement, you have to complement all the bits and add 1, and the add 1 part is accomplished through the carry in. Okay. Okay, comparator is when you want to compare 2 values to see if they're equal. Now this is kind of funny because we do this in your course CPU. This is how you implement your branch if equal instruction, right? But we don't do it this way. So the book says the way you should build a comparator is you take each of the corresponding pairs of bits from the A and B and you XNOR them together. XNOR is when, you know, it's true when the bits match, it's false otherwise. And then you fan all those into a big AND gate, and that tells you if the 2 values were equal. That's not how we do it in class. In the class one, we subtract A and B, and then we fan all of the bits of the subtraction into a big OR gate, essentially, right? See if the result is 0. Which way is faster? I'm unclear, but this is one way to do a comparator, right?
Because you don't need the adder here.
Right.
Only two gates and you're done.
Yeah, I think the reason why we do it with the adder in our CPU is just so we can reuse the hardware. But the real reason is it's because I've been using that same ALU for forever. We never really examined the impact of doing a comparator like this for the class. I'm not sure how much difference it would make. Okay, and then less than, though, this is the way that we do less than with our class CPU. So you subtract A minus B, and then you just look at the sign bits of A, B, and the difference, right? And so that's how your course CPU does it, right? So if A and B are both positive and you subtract and the result is negative, then obviously A was less than B, right? Likewise, if they're both negative and you subtract and you get a negative result, then that means that A was less than B, right? Okay. Okay, then shifter. So we did shifter. We have a shifter in our course ALU, and we gave you the ALU, so you might not have looked at it very closely. How does the shifter work? Well, as it turns out, shifters are actually pretty expensive. Specifically, a barrel shifter. This is a barrel shifter. A barrel shifter is a shifter where you take an input and you can shift it by any amount of bits you want. It's not just 1 bit at a time, but you can shift it by 5 bits or 4 bits or 31 bits, right? And that's how the one in your CPU works. The reason they're expensive is because fundamentally the way they work is you basically have your inputs come in, and then each output bit is controlled by a mux, right? And the inputs to each of those muxes are every possible shift amount, right? So for example, if the shift amount is 0, right, then this guy, y3 is going to be a3, y2 is going to be a2, y1 is going to be a1, and y0 is going to be a0. Of course, where y is the output and a is the input, right? But if the shift amount is 1, then y3, and this guy is shifting which way? This guy is shifting to the right, because, and the reason I know it's a right shifter is because if the shift amount is 1, then the most significant output bit is going to be a 0, because we're shifting in a 0, right? And I know that because that input to that mux is a 0. It's a hard-coded 0. And then the output, likewise, if I'm shifting by 1 and I look at the second most significant output, y2, that's a3. So a3 is then going to be flowing into y2, right? So this is a right shift by 1. And then if I shift by 3 bits, then y3 will be 0, y2 will be 0, y1 will be 0, and y0 is going to be a3, right? Meaning that I shift all the way to the right. So this is expensive, right? These muxes, there's 30, if it's a 32-bit shifter, you have 32 muxes with 32 inputs each. That's a lot of hardware. It's expensive. Which is why on an FPGA you can, if you use the tools that generate a soft core processor, which you guys have done if you took 313, you can actually select whether you wanted to put a barrel shifter in or not. Yes?
But why you cannot use just shifting register and just in AND clock have your AND bit shift?
You could, yeah, you could do it that way. That's a lot cheaper. In fact, that's what I'm going to show right here. That's a shift register. So a shift register is where you basically have a set of flip-flops, which can be connected. Well, one way to do it is to connect them in series, right? And so if you connect them in series and you clock it, then the data is going to flow out of the Q output of one and the D output of the next. So the data will be shifted by 1 bit each cycle. Right? That's a lot cheaper. But if you want to shift by 5 bits, it's going to take 5 cycles to do it. Right? That's it. That's the trade-off. Now you might say, wait a second. I thought you said in the last lecture that if you connect 2 flip-flops that way, wouldn't that violate the hold time? Because when you clock it, this input's going to change pretty darn fast. Yeah, it would. But the tools will take care of that for you. They're going to put a bunch of delay elements in between there to make sure the hold time isn't violated, right? So you never have to worry about it. The CAD tools take care of that part for you, at least, or they should anyway. Okay, then you can have, this is another shift register. Now this one looks a little bit more complicated, but it's the same idea. Each of these flip-flops is connected from, in this case, from left to right, right? Serially. The difference, though, is that we want to add the ability to load the shift register in parallel. So this gives you 2 operating modes. One is load the shift register in parallel in 1 cycle, or have it shift by 1 bit at a time. So to implement that, you add a mux to the input, where one of the inputs of the mux is just the same input we had before, just the output of the previous flip-flop. The other input to the mux is a parallel D input. I don't know why these are numbered from D to n-1, because that's the wrong order, but that's how they have it shown. n-1 should be here, and 0 should be here. But yeah, you get the idea. You can load them in parallel. So now notice I have this S out here too, by the way. The reason for that is the S stands for serial out. This is a parallel to serial converter. This allows you to load in parallel bits and then shift them out 1 cycle at a time. So in other words, when you're shifting the bits, instead of just like throwing away the bit that gets shifted off, you basically make that a top level output, and that gives you a serial output, right? And of course you have parallel outputs here as well. The Q's are parallel outputs. So you can look at the contents all in parallel, or you can look at 1 bit at a time as you shift it. Okay, and then shifters, I used to always get, like when I taught 212, students would ask me, like what are we using shifters for? What shift instructions, shifter circuits, what are they good for? Mainly they're used to implement multiply and divide. And they're also used for bit twiddling, bit manipulation stuff. But in the case of multiplier and divide, If you shift by n bits to the left, you're multiplying by 2 to the nth power, right? And if you shift n bits to the right, you're dividing by 2 to the nth power. So a shifter allows you to do a multiply and a divide as long as you're multiplying or dividing by a power of 2, right? Then no problemo. Just use a shifter.
Same way in decimal.
Right, yeah. Base 10, you could shift, you do it in base 10. Which is how I calculate tips at the restaurant. I just kind of shift it and then. But the problem is that if you want to multiply by a non-power of 2, then you still shift, same idea. The only difference is that you have to be able to shift by more than one shift amount and add the values together. So for example, if I want to multiply by 5, I know that 5, like if I look at 5 in binary, it's 1, 0, 1, which means that it's it's 4 plus 1, right? So 5 can be comprised as the sum of 2 powers of 2, right? 4 and 1, right? So all you got to do is shift by 2, and then shift the original value again by 1 bit and add the 2 together, and you get multiplied by 5, right? Divide is a little different, and I'll talk about divide here in more detail in a minute. Divide is not quite as straightforward as that, but multiply is just, again, you take the multiplier, right? The multiplier, and you convert it into a binary number, and for each of the bits that's 1 in that binary number, that's your shift amount. And then you add them up, yeah. Okay, so let's talk about that. Here's an example of that. So with multiplying, you've got a multiplicand and a multiplier, but they're interchangeable because it's commutative, right? But when you're multiplying, when you're building the hardware, you assign one of the inputs as the multiplicand and one as the multiplier. And the reason for that is the multiplicand is the number you're shifting. And the multiplier is used to figure out by which shifts you have to add together of the multiplicand, right? And so in this case, I'm taking 5 times 7. And so if 7 is my multiplier, 7 has 1, 1, 1, right? So I have to shift by 0, take the multiplicand and shift by 0, right? Add it. Then I take the multiplicand and shift by 1. Sorry, by 2. Sorry. No, 0. Oh, sorry, 1. Sorry, 1. Yeah, that's bit 1. Yeah. So that's bit 0, bit 1, and bit 2 are all turned on, right? So I'm going to shift by 0, shift by 1, shift by 2. And then I take each of those shifted values and add them up, right? So this becomes 5 plus 10 plus 15, right? All right?
Yes.
5, 10, and that's not 15. That's 5 times 2 to the second times 4. That's 20. Sorry, 20. Yeah, thank you. 20. Right? So that's 5 plus 10 plus 20. Right? And 5, 10, and 20 are just the 3 shifted forms of 5. When you add those together, you get 35. Right? So that part's, that's pretty easy. In fact, if you're writing code, like if you're writing software, and you're multiplying by a constant, if you know the number you're multiplying, if you know what your multiplier is, if it's a constant, then you don't actually have to run a multiply instruction. You can literally just do this in your, in your code. Yeah, like you can just that way you could avoid using the multiplier if there's a reason why you want to do that. Okay, so what about speeding up the multiplier? Well, the nice thing about multipliers is you can do this in parallel. And so the idea is that you have A, which is your multiplicand, right? And B is your multiplier. Now what you're doing here is you're taking the multiplicand, right? And if you want to take the multiplier and you're going to feed each bit of the multiplier into an AND gate, right, which effectively allows you to turn on or off the multiplicand as it goes into a multiplier, right? So in other words, what this is doing is it's taking each bit of the multiplier and it's using that to either switch on or switch off a copy of the multiplicand, right? So at the first level, what's happening is that you've got these adders. Now in this case, this is a little misleading because these blocks, these little shapes, these are actually just single bit adders, which always confuses me because when you see this symbol, this usually means like a multi-bit adder, right? But this is a single bit adder, right? So this whole thing, this whole row is basically one multi-bit adder. But what am I adding? Well, I'm adding, one input is going to be, basically just A, straight up A, either on or off, depending on bit 0, right? And then the other input is going to be another copy of the value of A, but shifted by 1 bit. So how do you implement that? Well, you might say, well, I don't see any shifting happening here. Well, the shifting is happening based on how you're feeding the inputs into the multipliers. Into the adders, rather, right? So you'll notice that over here, the least significant bit of the product is basically just going to be the least significant bit of it should be A0. It is A0. Yep, there it is. Yeah, A0, right? So that means that basically if the least significant bit of the multiplier is 0, then that's going to guarantee that the least significant bit of the product is 0, right? But then the next bit over, so bit 1 of the product, is going to be adding together, potentially adding the least significant bit of A with the next bit of A, right? Which is basically saying shifted by 0 and added to the shifted by 1 value, right? So if you look at the inputs of this guy, you've got, the right input to each AND gate is the B, right? So if you look at the left input here is going to be, it should be A1. Yeah, it's hard to trace that out though. A1. Yeah, here it is. Yeah, sorry, A1. Yeah, you're right. A1, right. There's A1, right? And A0, right? So what are you doing? Well, you're just adding A to itself, but you're shifting it by in this case, adding bit, bit 0 to bit 1. And so it kind of matches what you do here, like with the grade school multiplication, right? So in this case, A0 ANDed with B0 is this bit here, right? Which is just basically, there's no add, just an AND, right? But if you go to the next column, now I'm going to take A1 and B0, A0 and B1, and I add them, right? So that goes through just one adder. Now when I go to the next column, notice I have to add 3 things together, right? Which means the critical path here is going to go through these 3 adders, right? So this adder tree actually just matches up to that, right? The problem is that the critical path of this circuit is going to be whatever the most number of adders I have to go through here is, right? So one way to improve that is, so basically what I showed you before is this, right? It's kind of a linear chain of adders. You can take the same number of adders and you can rearrange them in a tree, and you can reduce the critical path by essentially reorganizing these guys. So the idea is, and actually, so actually, when you look at it, the way this is structured, you're going to end up going through, like this guy only goes through right? Or actually one and, no add. This is two adders. So it's just the ones in the middle where you go through the critical path. So actually, this is the structure that matches the sort of the grade school way that you'd multiply. So yeah, you've got multiplier 0 times the multiplicand, which gives you this guy, and then oh yeah, the main difference though is that, I'm sorry, these guys were, this is showing all, sorry, let me back up here. This is a 1-bit, these are 1-bit adders in this diagram, right? That's the difference. And then over here, this is showing just recomposing this as 32-bit adders, right? So it's just a different way to show it. I think the critical path, though, of this design is going to be the same thing. Is going to be the same as what we showed there. Okay. All right, so I got last topic of the class is division. So how does division work? Well, division is expensive because the problem with division is that if you think about how you do division in grade school, you've got your dividend, which is like the numerator, right? That's the number you're dividing. And then you've got your divisor, which is the denominator, right? And basically what you're doing is you're taking the divisor and you're subtracting it from the dividend. You're subtracting it multiple times, right? But the thing is that when you look at this, like if you take, this is 8 divided by, what would this be? 0, 1, 2, 3, 4, 5, 6. That's 64 plus 10, 74, I guess. 8 divided by 74, which is 9 with a remainder of 2. 8 times 9 is, what, 72, right? Yeah. So the idea is that we take this number and we put it underneath that number, that part of the dividend, right? Well, why do we do it? Why do we do it that way? Well, we just know that, when you're doing this as a human being, you know that we can take this and subtract it out of that part, right? But we know that just from looking at it, right? The way a circuit would have to do it is it would have to take this guy and move it all the way over to the left and try to subtract from the dividend, and it would find out, oh, I can't do that. Shift. Right? I can't do it. So I'd have to take this number and subtract the shifted form of the divisor, but I'd have to shift the divisor all the way to one side initially, try to subtract, and then find out, oh, I can't do that because that gives me a negative number, and then you got to try again. So this is what's called a restoring divider. It's a restoring divider because it kind of works by trial and error. It has to figure out what part of the dividend can I subtract the divisor from? And I have to do it by trial and error. So I'd have to start out over here, and then I have to keep moving that divisor to the right until I eventually line it up under this part where I can subtract 9 minus 8 and get 1. So this number has to be positive or 0, right? Right, now this is binary, so either it's 1, like when you look at the quotient, it's either each digit's going to be 1 or 0. So 1 means that I was able to divide that, I was able to subtract that part from that position. But what's not shown is the leading 0, 0, 0. So there's 3 leading zeros that aren't being shown here, and those are coming from the fact that I shifted the divisor too far over and I got a negative result. But that's just not, you never show that when you do it by hand. You see where I'm going with this? So that's basically the idea with a divider, is that you have to shift the divisor to the left relative to the dividend, right? Or you can shift the dividend to the right. You can either shift this guy left or you can shift that guy right. It's up to you. But either way, you got to start out with the divisor looking like a bigger number than the dividend. Then you subtract. If the result is negative, you undo, and then you shift again. Every time you subtract and you don't get a negative number, then you stick a 1 in the corresponding position on the quotient, right? And then eventually you end up with just the remainder, with whatever's left over, okay? Okay, so, so how do you do this in a circuit? Okay, so the problem here is that you can't do it with just adders like we showed with the multiplier. You have to use these boxes. These boxes. And the way the box works is inside this box, you have a, okay, that's weird. That B should be negated. Am I not? Oh, yeah, it's not showing up. Oh, it is. Oh, sorry. It is here. Sorry. You see how that B is negated at the top? Okay, so what's happening is that we're taking B, which is the divisor. It's the smaller number, the denominator. B is the denominator. That's the divisor. So B is the value that this guy. And we're subtracting that, right? So to subtract it, notice how they negate B, not B, 1, 2, 3, and they have this 1 coming in. That's the carry in, right? So you put a carry in and you negate B. Why? Just because we're going to subtract it, right? So each one of the rows of these guys is subtracting B. And B is fixed. B is just always the same. Or actually negative B. You take negative B and you just feed negative B down. Okay? So B, you just keep subtracting B over and over again, right? Now the difference is A. A is the dividend. That's the bigger number. Okay? So what do we want to do? We want to shift A to the right relative to B. Now you might say, wait a second, whoa. You didn't do that here. In this case, the divisor, notice there's a 1, 0, 0, 0, and what's implied is that there's a 0, 0, 0. There's 3 more zeros after this, right? Notice the divisor, when I subtracted the divisor, it was shifted to the left relative to this, so it was made bigger. Whereas in the hardware, I'm doing the opposite. I'm taking the dividend and shifting it right. And how am I doing that? Well, the dividend is A, so what's happening is that the first time I subtract A minus B, I actually am just subtracting 0, 0, 0, A3, meaning that the only thing I've got left of A is the most significant bit, and it's all the way to the right, meaning that I took A and I shifted all the way to the right. So basically it's 0, 0, 0, A3 minus B, right? So that's my first attempt at subtracting. Now what this circuit does is it says, there's a mux here. And the mux basically says after you subtract, if the result is negative, then you restore, meaning you switch this mux to 1, which feeds the original R through. So the R, which stands for remainder, which is actually the result of the subtract, this difference, that's flowing down. And as it flows down, it's going to stay the same. Right? It's going to stay the same if the subtract failed, if it was negative. If it was non-negative, then you switch this mux to 0 and you pass down the difference, right? The subtract, just the difference, right? So that's all you're doing, is you're just basically subtracting, and you're either passing down the difference or restore it by switching this mux and just passing down the original value, right? Yes?
So n is the sign bit of the result of our addition.
Yes, and Q. So there's this quotient comes out here too. So if the sign bit is 1, that means it's a negative, then you negate 1 and you get a 0, meaning that if the result of that subtraction was negative, then the corresponding quotient bit is 0, right? That's why we negate, okay? So, so that's pretty much it. Now the only other detail you have to understand is that the shifting, how do we get the dividend and shift it? We have to shift to the left, right? I mean, right? Because normally you got to shift the divisor to the right, or you have to shift the dividend to the left. You got to choose one. In this case, we're going to shift the dividend to the left, right? So the way you do that is when you pass the value, this is kind of neat how this works. When you pass the value down, which is the remainder, right? Again, this value, what I'm talking about here, is this value, these intermediate values. These values, as you go down, you basically see how these wires go diagonally? You shift it as you pass the value down. So whether you're passing down the difference, the subtracted value, or the original value, because you restored it with this mux, these diagonal wires are going to shift left. Meanwhile, A2, which is the next to most significant bit of A, is going to work its way in. It's going to sneak in here. It's going to get shifted in, right? And then A1 and A0, right? So basically, you just take these differences and you keep shifting it down. And then by the end, you'll have the quotient bits will come out, which are just basically whether the result of the subtract was negative or positive. Whether you restored it or not, the Q bits will record whether the subtract was successful or not. And then whatever gets passed down will be the remainder, which will get whittled away little by little. Starts out as the dividend, but then you're subtracting, 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 and by the end it'll be the remainder, right? So that's how you can build this with essentially an array of adders, which are actually subtractors with a mux. Now, you might say, well, that doesn't seem that bad. I mean, compared to the multiplier was essentially an n squared array of adders, right? Yes, but you've got this mux, restoring mux at every level, right? So there's more delay here. So it's slower than the multiplier because you have to restore. That's the difference. So I have an example. I have an example I worked out here. 11 divided by 5. So 11 divided by 5 is 2 with a remainder of 1. And it's 2 plus 1 over 5. 2.2, right? So the way you start that out is, I'm not sure how clear this will be, but so you basically have 1 is the shifted, the shifted numerator, the dividend. Why is it 1? Because the most significant bit of A was 1, right? But it's all the way to the right, right? And then that 5 is always the same 5, right? So you're going to start out 1 minus 5 is negative 4. Because it was negative, that Q bit will be a 0, right? Because the sign bit's 1 means the inverted sign bit is 0, right? Then you're going to restore it, meaning that 1 will pass down. You restore it, meaning don't cancel the subtract. Just leave it as 1. But as you pass it down, shift it. So now it's 2. But we're also going to shift in A2. So but unfortunately, I think A2 is just 0. So yeah, no big deal. So that's just 2. 2 minus 5, still negative. So you take the 2, and that's going to become 4 as you go down. It's going to be restored, first of all. Then it becomes 4. But then we add an extra 1. Why? Because of that 1. We shift in that 1. So basically, we've got 1, 0, 1. That 5, right, is from having shifted this by 1 bit now. So 5 minus 5 is 0. Good. So that quotient is 1. And now we're going to not restore, so that 0 gets passed down. But, so that 0 shifted by 0, 0 shifted is still 0, but got an extra 1 in here, right? So that becomes a 1, right? Just because of this bit, right? So 1 minus 5 is negative 4. Nothing we can do there. So that's a 0. We restore it to 1, right? And so our remainder is 1. And our quotient ends up being 2 because the only subtract that actually was successful was that third one. Right? So that's how a divider works. It's not really that bad if you understand what's going on in the circuit. The only thing that I think is confusing about this is the fact that the dividend is being shifted to the left. The dividend, right? A is being shifted to the left, right? Makes sense? As opposed to the way you do it in grade school, which is where you take this guy, the divisor, and you shift it to the right as you go. As you progress, you shift it to the right, right?
Well, that's really important. The important thing is that they're relative position.
Yeah, it's the relative shifting, right? Yeah, exactly. Yeah. So that's the divider, and that's all I've got. Oh, yeah, I'm 2 minutes late. Sorry. Okay. If you have any questions about the review sheet or any of the previous quizzes, let us know. And like I said, don't forget to take those 3 quizzes. That'll help you practice for the final. And check out the review. Thank you. Have a great break. Merry Christmas.